Testing on YouTube. Testing on YouTube. Testing on YouTube. All right, maybe a little bit. Testing on YouTube. Testing on YouTube. Okay, I think that's perfect. All right, let's test on X. Testing on X. All right, X works as well. All righty, let's get started. Welcome everybody to another Hoopost stream. This one's called Language Guided Rewards. How's it going, James McLean? So we got a little bit of an origin story for this particular stream. It all starts with this podcast here called Robo Papers. I think it's more of an X podcast than a YouTube podcast, but they started posting a bunch of their stuff on YouTube, so highly recommend it. It's a pretty great podcast. They talk to a lot of the authors of these robotics papers, and I listened to this one yesterday, and they talked with this guy, the famous Stone Tao of Manyskill, and at the very end, they ask him, what's your favorite robotics paper right now? And he mentions this one. So that's what we're going to be talking about today, is this specific paper recommended by someone who definitely knows their stuff in robotics. This is called Rewind, Language Guided Rewards Teach Robot Policies Without New Demonstrations. It's a little bit older, 16 May 2025, but very interesting paper. There's kind of like some ideas that touch on some other things, some other papers that I've seen. So I think it's going to lead to a pretty interesting discussion. So that's what we're going to be doing today. How's it going, Mark B? Happy Friday. All right. So what does Rewind stand for? Rewind stands for Rewards Without New Demonstrations, right? So learning robot manipulation tasks solely from language instructions without per task demonstrations. So most robotics right now uses things like reinforcement learning and imitation learning. And imitation learning in particular usually is done via these expert demonstrations, and then you effectively are behavior cloning from those expert demonstrations. Reinforcement learning is a little bit different because you're kind of collecting the experience using the policy and then training on that collected experience, usually done in sim because it's almost like dangerous to try to collect robot experience using a real robot. But Rewind does something a little bit different. So it's kind of more similar to imitation learning, where you're going to start from a small demonstration data set, right? So what is that going to look like? It's going to look something like this, right? So you're going to collect a sequence of observation frames, or that's just a kind of fancy way of saying a video of a robot or a trajectory, right? Kind of robot going and grabbing something. And you're going to have a natural language task description, right? So maybe a couple sentences that describes what happened in that particular video. And the whole point of this paper is that demonstration data set is going to be very small, right? And kind of we all generally understand from machine learning and deep learning that the kind of small data sets generally don't work super well, and training on that, you're generally going to overfit and it's not going to perform particularly well. It's not going to generalize beyond that data set. It's also probably going to be very fragile to the, for example, lighting or the object that you're using or the robot embodiment. So this paper is trying to solve that by using that small data set, in addition to some other little tricks, to create a data-efficient language condition reward function that labels the dataset with rewards and a language condition policy pre-trained with offline RL using these rewards. So it's like this 3-part process, but it has some very awesome data augmentation based on kind of time, which is going to eventually be the kind of theme of this. How's it going? Open Room XYZ. Okay. Here in blue, we have kind of the results of the paper. It beats baselines by 2x in simulation, improving real-world pre-trained by manual policies by 5x. Evals are kind of broken for LLMs. They're even more broken for robots. Comparing things on robots is very, very difficult. Usually it's different embodiments. The tasks are different. The implementation matters a lot. So your implementation of a baseline might be very different from the official implementation of a baseline. So don't read too much into this. I think the most important part of this paper is kind of this interesting multi-phase training process that uses kind of this natural data augmentation. Okay, so let's go into the introduction here. Small data sets train LoRA, generate big data set. Yeah, this is in that theme, right? It's like data augmentation is how do I take a small amount of data that is kind of very narrow, and how do I augment it so that it has a much larger variance, covers a larger part of the state space, right? So this is within that theme, Open Room. All right. For deployed robots to learn new tasks in the wild, they need intelligent teachers. Okay. I think that's just a good high-level kind of intuition there. Large-scale imitation learning is where humans provide demonstrations for each new task, right? So for example, you might have seen those Tesla Optimus videos where you have like this kind of like warehouse and they have like 10 different people teleoping the Tesla Optimus, right? So that's kind of large scale imitation learning where you have people just teleoping robots collecting gigabytes of data just day in, day out. But we know just from kind of the news that it's not working super well, right? So all these robotics companies, they kind of went all in on imitation learning. All of them have this like teleop kind of solution, but you know, it's been a couple years now and nobody's really kind of shown an outrageous kind of performance from that. So we're starting to see the cracks in imitation learning and starting to see that, hey, you can't just naively scale up imitation learning and VR teleoperation and get something that kind of works for every single situation. So reinforcement learning is something different that people have been trying to bring into robotics. It's been part of robotics for a long time, but this is something that people are exploring a lot, for example, for these walking controllers, right? So all those demos that you see of the robot walking over things or the robot balancing and you kick the robot and it kind of like stays upright, that's usually done with reinforcement learning in simulation. And this offers a more autonomous alternative by using reward functions as teachers, allowing robots to learn through interaction. So the reward function is the teacher in reinforcement learning, right? So the reward function for a walking controller might be how close is your center of mass to the floor, right? So if your center of mass is very close to the floor, that means you're on the ground and it's bad. You're going to get 0 reward for that. If your center of mass is higher up off the ground, that means you're walking and doing stuff, so you're going to get a high reward for that. If your center of mass is moving forward with some velocity, that's also going to give you higher reward. So this reward function, which has been crafted by a human and usually tuned, there's all kinds of little magic numbers and hyperparameters inside these reward functions, those act as effectively the teacher. But manually designing these reward functions demands substantial manual effort and domain-specific expertise, and it's also not really super intelligent, right? It's like this kind of frozen thing that you can hill climb, and you can get really cool demos, like robots being able to balance and stuff like that, but you're not going to get to kind of like a fully generalizable kind of like robot using those type of RL approaches, right? So the two approaches, I think this paragraph is a nice summary of the two basic approaches in robotics right now. We have imitation learning and reinforcement learning, and both of them have their limitations. I would say imitation learning is a little bit more popular in manipulation, and reinforcement learning a little bit more popular in locomotion, but both of them are running into problems. Okay. Open Room XYZ. One thing that they could do is virtualize robotics, basically generate the body of a robot procedurally and then train networks that have to generalize between bodies. Yeah, that's already kind of happening. So most simulations, for example, in reinforcement learning, we'll have domain randomization, right? You could also call it procedural randomization because it's randomization that is happening based on some procedure that someone wrote. And usually, for example, they'll change the lengths of the links, right? Or they'll change the friction coefficients, or they'll change the different variables of the controllers within the simulation. So by having a broader distribution of environments, the policy that is learning from those environments via reinforcement learning is more robust to differences, so that whenever you deploy this policy that's been trained exclusively in sim into the real world, it'll zero shot a little bit better, right? So you can get that sim to real zero shot that everybody loves, where as soon as you take this policy trained with reinforcement learning in simulation into a real robot, it actually works. Okay, but let's go back to this paper. So we're going to skip the kind of generic introduction section, and we're going to go straight to the explanation of rewind here. So they're going to be wrapping all of this in a Markov decision process, pretty kind of standard stuff there. I apologize about that. Every time I start yapping, I just, like, my nose starts running just because I'm spending all my time kind of talking out of my mouth. So you can see all the basic stuff here. We got a policy pi0 neural net parameterized by parameters theta that produces actions given some observation and some z. Z is going to be your language instruction. That's going to be your task description, basically just like a sentence that describes the task. The policy is optimized to maximize rewards using a learned reward function. So that's really the important part here, right? Is that a lot of times in classic robotics and even current day robotics, these reinforcement learning is using a hard-coded reward function, right? Some reward function that has been designed. In this one, we're instead going to be learning this reward function, right? And this reward function, you can see it's also a neural net. You can see it's R here, parameterized by psi. So the parameters here are theta, the parameters here are psi. And it's going to take in a sequence of observations, O, and a Z, which is, again, the language instruction, and it's going to produce a single reward, right? So given a frame sequence O1 to T and an instruction Z, it outputs per time step estimated rewards, right? So, for example, you can see that the policy, it only takes the observation at time T, and it produces the action at time T, right? So it's kind of like a one-frame kind of thing. And you can do multiple frames here, right? You can condition on a history of frames, but in this case, it's just literally, given this observation, what is the action? The reward function has the full observation sequence. So you can see it's taking in the full observation sequence, and then it gives you the time step just for that, or the reward just for that time step. Okay. How's it going? 42. All right, so the small demonstration data set, right? So again, the whole point here is that we're going to figure out how to augment a small imitation learning data set. And that small imitation learning data set, they're going to call it D-demo. And it's going to consist of 15 to 20 tasks with about 5 demonstrations each. And this is something that you could collect one person in kind of one day, right? So depending on how many tasks you already have set up, right? Maybe you have like a pick the ball, put it in the cup, take the ball out of the cup, move the cup over here, right? Open a drawer or something like that. 5 demonstrations each is not a lot of data at all, right? So you're getting a very, very narrow slice of each task. We define a task as unseen if it requires a novel action sequence, its distribution of image observations has changed, or needs a new language instruction. Okay, so this is, I guess, a little bit nebulous here, but the definition of task is a little bit nebulous as well. All right. Learning the reward function. We regress directly to per frame progress with a dense 0 to 1 normalized reward for policy training. Okay. So what they're saying here is that this learned reward function, what they're going to try to get it to learn is the per frame progress. So what this actually looks like is effectively like this, right? So here's the rewind reward. Here you have the time. So this is the rollout or the trajectory. It starts here. This is basically frame 0, and then this would be the end frame. And this is the kind of progress, right? So you can see that initially the robot starts off, it hasn't done anything, and then as it kind of moves the hands closer to the objects, the reward function says, oh, you're getting close, and it kind of increases the reward. And then as you try to do the thing, in this case, it's an unsuccessful, but it kind of goes down, right? So you see that, okay, there's less and less reward, you're not actually completing the task, and so on. So rewind failure example. But if this were to succeed, you would see basically this kind of reward function goes up and up and up, and eventually it hits 1.0, which is kind of like you have completed the task. And I guess at that point, the policy kind of terminates or something like that. Okay. So you can see here the loss, our reward prediction loss, right? So because you're learning this reward function, that means you need some kind of loss function to push gradients into this neural net, right? Here, that's the parameters of the neural net that define this reward function. So this loss is simply going to be the difference, right, between the reward that you're getting and then this progress, right? So if you're at the very end of the time, it's going to be t is going to equal big T. And if you're at the very beginning, t is going to basically be 0. So you want to, it's almost like you're trying to guess where along the trajectory you are, right? Are you right at the beginning of the trajectory, or you end at the trajectory? And we're kind of assuming that kind of the reward is increasing as you get closer to the final frame in the trajectory, right? So your demonstrations are basically starting from not working to done, and then you end it. Damn, OpenRoom XYZ, you're popping off here with this comments. One thing that I thought is that maybe generating real data may be easier than generating it with AI or in simulation. The hard part about real data is that it's much more difficult to parallelize, right? So think about coming back here to the imitation learning situation, right? If you wanted to collect 10 times this amount of data, right? Let's say you wanted 150 tasks with 50 demonstrations each, you would probably need to have 10 times more people, right? If you wanted to collect 100 times more of this demo data, you would need 100 times more people. So there's kind of like this linear scaling with the size of your demonstration data set or your size of an imitation learning data set and the amount of time it takes and the amount of humans it takes to collect that data. So that's why simulation is so popular, because for roughly the same amount of human time, as long as you can increase the compute budget, you can drastically increase the size of the data. The problem with that is that the simulation data set is not the same thing as the real data, so the kind of amount of juice that you can get out of simulated data is generally not the same quality as what you can get from a real data set. So real data sets are better than simulated data sets, but real data sets don't scale. Person exploring infinite spaces. You can have 100x the cameras in the same place. Okay, interesting. So OpenRoom XYZ, you're talking about you may not be able to parallelize the demonstration, but maybe you can parallelize the multi-view, which is actually an interesting observation, because that's kind of what we're going to be looking at this paper. So we're not going to go, maybe we're just going to sneak peek this right here, but in this paper, they use kind of that idea where they have the same demonstration being filmed from multiple viewpoints, and that is a way of kind of augmenting a data set, right? Because you kind of know that underlying this sequence of frames and this other sequence of frames, they're both coming from two different views, but they're the same sequence of frames. So that multi-view as a way of kind of increasing the amount of data that you can collect in the real world is definitely an idea. All right, let's go into here, incorporating diverse data. So in addition to this small demonstration learning dataset, they're also going to be using the OpenX dataset, which is specifically OpenX trajectories with object-centric language instructions, e.g. pick a Coke can from a fridge, drag the circle to the left star, and this is about 356,000 trajectories with 59,000 unique task strings. So there's a combination of two datasets here, and you can see it here in Figure 2. They have their little tiny demo dataset, and then they have the OpenX subset. And you can see that the OpenX subset has a lot of different embodiments. You can see here the KUKA robot, the Franka robot, the UR robot. So there's a lot of different robots. All of them are kind of one arm pick and place. So you can see every single one of these is a single arm doing some kind of pick and place. You can see some variety in the gripper cam. Some of these are third person viewpoints. Some of these are kind of more gripper cam viewpoints. But this is kind of like the pre-training data set, right? It contains the large variety of environments, lighting conditions, simulations, and tasks, right? So this is maybe 5 or 10 tasks. This is going to be like hundreds of tasks. Actually, they literally say it. They literally mention it. What is it? It's 59,000 task strings. So that's a lot of different tasks. And it says task string, so a lot of these tasks might be more similar. It's just that they have a different string, which ends up going into the model, right? So this K here, or the Z, that you're using to condition your reward, and you're also using to condition your policy, right? So both your policy and your reward function are taking in this task string. All right. Video and language augmentation, and this is where we're going to start getting into the part of the paper that I think is really cool. Both video and language augmentations are used. We call the video augmentation video rewind and the text augmentation instruction generation. So let's start with the text augmentation because that's the easiest one to understand. So the text augmentation is you generate 5 to 10 additional language instructions for each task in DDemos by prompting an LLM. So anytime we sample an observation sequence O1 to T, its instruction Z is uniformly randomly sampled from all available matching instructions generated or original. So what they mean here is that for every time they sample a batch of data from their demo data set, there's going to be some sequence of observations, and then there's going to be some language instruction or description of the task, right? So dispose trash. So the language space augmentation is going to simply consist of taking a frozen LLM, probably like GPT via API, and it's going to effectively rewrite that language instruction. So we've seen this over and over again, right? Rewriting image captions, rewriting math questions, right? So basically just using the fact that these LLMs can infinitely kind of recombine the words inside any sequence of text into a different sequence of text that has the roughly similar semantic meaning. All right, so throw away garbage, put waste in can. Those are effectively equivalent to dispose trash. So by augmenting this language space, you now have a much more rich mapping between your robot trajectories and kind of the world of language, right? So rather than having this kind of one-to-one mapping where it's like this one trajectory maps to this one sentence, you now have this one trajectory maps to multiple different sentences, right? So that's kind of standard language augmentation that kind of everyone is familiar with now. The second and cooler type of augmentation, and this augmentation is going to be in the video space, is going to be what they call video rewind, this is the core idea. This is like the core awesome idea in this paper. So they randomly rewind videos. If we rewind the video for a few frames right when the robot grabs the cup, it now looks like the one in which the robot attempted to grasp the cup and then dropped it. So the observation sequences mimicking failed policy rollouts, and the key thing here is that they learn to decrease the reward when necessary. Okay, so this is a little bit harder to understand, but we're going to see what it means here in this figure. So in the video rewind, what they're going to do is their data set of 15 to 20 demonstrations only contains successful trajectories, right? So you're not collecting failed trajectories, right? That's something that people do in imitation learning too, right? Where they might collect, this is me putting the ball in the cup, and then I'm going to collect one where I grab the ball and I just put it on the table, right? And that's going to be my kind of failure trajectory. But that's kind of annoying, right? You're going to have to collect that too. So now you come back to the problem of it's very annoying to have to kind of like physically create all this data. So by what they do here, which is pretty clever, is they start with the first 4 frames and then they literally just rewind, so that they say, okay, we're going to go from frame 1, 2, 3, 4, and then we're going to go back to frame 3 and back to frame 2. So what this means is that now I took my one successful trajectory and I created this new trajectory which is slightly different because the reward is going to go up and then suddenly the reward is going to go down because like it's going towards the cup and then it doesn't actually grab the cup, it just backs away from the cup, right? So you've now found this augmentation strategy in the video space that allows you to effectively create infinite unsuccessful trajectories using just a small amount of successful trajectories, right? And this is really important because anytime you're learning something with a neural net, right, and in this case, you're learning the reward function with a neural net, you don't want something to be the same every single time, right? So if you were trying to learn this reward function using exclusively these type of successful trajectories, the reward function would always kind of be monotonically increasing. So it would be very, very difficult for your reward function to then output something where the reward isn't just monotonically increasing, right? You want to have examples that are pushing gradients into your reward function where the reward goes up and then it goes back down. And if you don't do that, then that's probably never, your reward function is never going to do that. So that's a very good idea. And I think this is the most important idea in the entire paper. Okay. So here's the loss function specifically for the rewind, and then ultimately you can scroll down here, and the final loss function, which is used to push gradients into this learned reward function, is going to basically be the combination of both of these. The progress reward function, right? Here you're taking in the full observation sequence, and this language instruction, and also this rewind loss, which also has the same inputs. And ultimately, right, you're sampling these, just to explain kind of this equation here, right, you're sampling these observation sequences and the language instruction from the demo data set and the OpenX data set, and the whole point is that you want to find the psi here, which is, again, the neural net parameters for our learned reward function that minimize the expected value of these losses, right? So you want to make the loss go down, so you want to find these values that minimize these loss functions, and that's the objective. That's the final objective that you're using to learn this reward function. Okay. That's an interesting trick. Yeah, I thought it was pretty cool, and it was so cool that I had to see if it reminded me of some things, and I went ahead and I kind of looked at some other papers that have this idea. So here's another kind of a little bit of an older paper as well. This one's called Retro Actions, Learning to Close by Time Reversing Open Videos. And this is effectively the same idea. Not in robotics, this is more for video understanding, but it's a very, very similar task. So video transforms that result in class homogeneous label transforms. These are video transforms that are consistently maintain or modify the labels of all videos. So for example, horizontal flipping, time reversal, and their composition. Okay. So what they're talking about here is there's label altering video transforms and non-label altering video transforms. So this is kind of like a needlessly formal way of describing some augmentation in video space that preserves the label. So what they're saying is that there's going to be ways that you can modify this video where the label stays the same, right? So if you take this video and you rotate it by 1 degree, it's still going to be the same video of disposing trash, right? So rotating the video frames is a, let's use the terminology here, is a non-label altering video transform, right? If you took this and then rewinded it, then that would be a label altering video transform because it no longer represents disposing trash, because now it represents kind of going into the trash can and grabbing something out of the trash can, right? So now it's like almost like the opposite. So that has now altered the label or the task instruction, right? So we are interested in LATs, or label altering transforms, where the application of the video transform T to every example of the given class results in transform labels belonging to the same class, and we call this class homogeneous LATs. So the class here, this is referring to the fact that this is an older paper, and they're doing video action recognition, or basically taking a video and then classifying it into one of like 100 different possible things, right? So like this is kind of like old school deep learning, where you're not going straight into text token space, right? Like if you were trying to solve this using current techniques, you would use a vision language model, and the vision language model would literally output the token. So there's no explicit classes in a vision language model, right? It's outputting tokens one by one, and the sequence of tokens that comes out tells you what's happening in the video. But 5-10 years ago, what you would have to do is you would have some explicit list of classes, maybe 100 classes, kind of like ImageNet, right? Where it's like, here's the specific classes that it is, and I just want to classify this video into this class or classify it into this class. So that's why they use the terminology of class here, right? So class homogeneous LATs are LATs that if you apply them to the video, they don't change the class. It's still a video of cooking, right? Okay, let's keep going down here. So here are the different class transforms. Hello, Hoopo. How's it going, Ed? So for example, you have horizontal flipping, time reversal, and their composition. So you have the original video, sequence of frames, 1, 2, 3. Horizontal flipping just flips them, right? And this is actually not going to change anything, right? If you horizontally flip, it's effectively the same exact video. So it ends up being the same exact class, or in our context, it ends up being the same exact task description, right? The more interesting one is this one here, time reversal. When you reverse the time, now suddenly you're going to basically almost like apply an inverse to the task description, right? So you could say, okay, if I reverse the time on closing or opening, then it now becomes closing. If I reverse the time on pushing something right to left, now it suddenly becomes pushing left to right, right? So these are non-class homogeneous LATs, and you can have a combination of those as well, right? So I just wanted to show these, right? Because, for example, this paper here only uses the kind of time reversal trick, right? But they don't use some of these other augmentation strategies. So it just means to me that even though this paper got pretty good results, they're still not using all of the different data augmentation strategies that are available in the video domain. Okay, I think there's also this paper here. Yeah, this is basically kind of a very similar paper that is doing these kind of augmentations in video space for video action recognition. So constraining the model predictions to be invariant to diverse data augmentations effectively injects the desired representational invariances into the model that helps improve accuracy. So this is just like a nice formal way of describing why we want to do data augmentation, is because ultimately the model, you want this model to be robust, or you want it to be able to generalize outside of its training distribution. So by augmenting the input data, right, you can increase the variance of the training distribution so that whenever the model is deployed to some real-world use case, the test case is within the training distribution, and thus your robot is able to generalize, right? So ultimately, you're just trying to improve accuracy by increasing the size of that training data set via data augmentation. So I'm not like super interested in most of this paper. I just kind of mainly wanted to show you guys the same transformations here. So you can see representational invariances for video action recognition. So geometric invariance, photometric invariance, temporal invariance, and scene invariance, right? So in the case of action recognition, this video of this guy playing tennis and this video of a different person also playing tennis on a different court with a different angle, they're still both videos of tennis, right? So you want both of these videos to map to the same class, right? Even though photometrically they're very different. And here we see the same things again, T half, T drop, T reverse. So kind of very, very similar to this thing here, right? Time reversal, horizontal flipping. In this case, you have T half, which is like duplicating. So if you have 1, 2, 3, 4 frames in your input observation sequence, you can just do 1, 2, 1, 2, right? So you cut it in half and duplicate it, and it's still just a video of someone playing golf, right? You can't really do that here, but I think there's things you could do that are similar to that. 3 different temporal transformations, T half, T drop, and T reverse. And here's the exact definition. So T-half and T-drop is an invariance to partial temporal occlusion, which enforces models to recognize actions even with partial evidence. So what would that look like here? So one thing you could do is in your, as you're sampling batches to train your learned reward function, you could simply drop out some of these frames, right? So rather than feeding every single frame, you could maybe take this third frame and just get rid of it. Just put a bunch of zeros in there, right? So that's something that's kind of like this, and it enforces an invariance to partial temporal occlusion. So if you were to deploy this robot in the real world and maybe it runs into some camera issues that you miss a frame, your policy is going to be able to handle that missing frame because in training it had data sets that had missing frames, right? So another one here, invariance to speed. The same action can be performed at a different speed. So in video action recognition, a video of someone playing tennis and then a sped up video of someone playing tennis should both map to the same class of, hey, I'm playing tennis. It's a little bit more complicated for robotics because the speed is kind of calibrated, right? The inference speed, the amount of time it takes for your model to perform inference, and the frame rate of the camera, the kind of control frequency of your control loop that's actually running on the motors. All of those things are a little bit more tuned. So if you were to just arbitrarily speed up these robot trajectories or slow them down, I don't think that's going to be a good data augmentation method for robots, just because the frame rate or kind of like control speed of robots is a little bit more fragile. You have to be a little bit more careful there, but it's a possible idea. Someone could explore that. Invariance to temporal reverse order. Cyclic order invariant actions such as push-pull, punching bags, and many instrument plane actions are invariant to reversed order. That's not as much the case here, but it's basically the same idea, right? The same idea that like, hey, if we're learning this reward function and we know that the robot starts and it hasn't picked the ball and put it in the cup, and then at the end the ball's in the cup, then I can basically do this fancy video reversal and then create these unsuccessful trajectories where my robot goes and reaches towards the cup and then suddenly it goes backwards away from the cup, right? So it's kind of that same idea. But the main difference here is that I think this is a much denser signal, right? So like, for example, here, right, you reverse the action, right? You have the reverse sequence, but it's still mapping to the same class, right? So if you reverse the time, it's kind of like you're just augmenting the data set by saying, okay, here's the input and then here's the output, which is the class, and then we're going to have this the rewinded input and it's going to map to the same class. So it's a type of augmentation that it's not super dense, if that's that makes sense to you guys. Versus this is much more dense because your reward function, your learned reward function, is kind of regressing to a continuous value, right? You're not just predicting a single class out of some set of discrete classes. You're literally outputting a dense 0 to 1 normalized reward for policy training. So that means that you can get a much kind of denser data augmentation using this video rewind in this specific application. I'm yapping. Let me take a break here to answer some Open Room XYZ's questions. Time reversal only works in some cases, like moving sand would not work like that. Yep, you are correct. This type of data augmentation has some kind of like built-in biases. You could not kind of just naively apply it to everything. If you had a robot that was like scooping up sand and putting it somewhere else, right? You couldn't reverse that and then create a like how to unscoop sand, you know, because you can't like Jedi force grab sand. Okay. How do you map the action space and how to make this general basically needs to be learned from context? Okay, I think that's a good kind of segue into the next part of this, because up until now, we've basically described how to learn this reward function and some augmentation strategies that allow you to learn this reward function from a small data set. And that's really just the first part of this model, right? So the first part of this pipeline is taking these data sets, augmenting them. So you see these arrows here, they're basically going in here. Here are the two different types of data augmentation. You have your instruction or text augmentation, then you have your video augmentation. You use that to train this reward function, right? This reward function consists of these pre-trained backbones, so they actually mention them here. The specific ones they're using are Dino 2, Dino V2 for image encoding. So this is what's taking your image and turning it into this image information here, this image embeddings. And then you have all mini LM L12 V2, which is kind of a weird one. I don't know if I've seen this one a lot, but kind of an interesting choice. But that's the text encoder, right? So basically they have the frozen text encoder that's going to take your raw text string and turn it into this language embedding. And then you have your frozen image encoder, which is going to take in your observation sequence and turn it into these image embeddings. And again, Dino V2, right? So every paper that you see that has Dino V2, you could just literally drop in Dino V3 and you're going to automatically get a bunch of free wins. So that means that the results here could be even stronger if they use Dino V3. But ultimately, these embeddings coming from these pre-trained frozen backbones are going to go into this transformer here, which they're calling a cross-modal sequential aggregator, just kind of like a fancy kind of term, to be honest, but it's basically just a transformer. It's going to output this sequence, right, sequence to sequence, and that sequence is going to go into an MLP to produce a single number, which is that reward, right? So ultimately, your reward function is taking in observation sequence and text describing the task, and it's going to output this single number between 0 and 1. And that's going to be a reward for that specific time step. Okay, so now we have this magical reward function, which gives us our reward based on an observation sequence and a text description. Now what do we do with that, right? So now this is where we actually start doing some robot learning, right? Because ultimately, the neural net on our robot is this one here. It's not the reward. We don't actually care about this reward function when we're actually using our robot, right? What we want is this policy, right? That's what we want, because that's what we're actually going to be running on our robot. That's what's actually taking in the observations and the that are actually occurring in the real world, and then outputting some action that is then used in the next frame, right? And we're going to train that policy first by using our reward function. So you see here this kind of repository, this data. This is usually kind of this type of symbol usually represents kind of a database. So in this case, this database is basically just your data set, right? So usually this is called the replay buffer, right? And that's why it's called offline RL. In offline reinforcement learning, you are not creating any more data, right? All the data has already been created. It's sitting in this data set, or in this kind of like database called the replay buffer, and you're just sampling from that, right? So you're basically you just keep sampling kind of the same stuff over and over again. But it's not always the same because you're applying augmentations to it. So jitters, maybe flipping the images. So it's slightly different data, but it's basically just you're sampling from the same data set. Okay. You sample individual stuff from that data set, and because you now have this frozen reward function, you can get the reward. So now you have the full tuple, right? So the tuple refers to this thing here. OT, AT, R hat T, OT plus 1, and Z. Let me blow my nose real quick. All right, so Ed is telling us that this weird text encoder that they're using is 22 M params, and Dino V2 is also 22 M params. Okay, so you're saying that this is basically one of the smallest text encoders that they could find. So, all right, that makes sense. Basically, the reason they chose this text encoder is because it's very, very small, because I assume they wanted to kind of run this on a very small edge compute, so they didn't want to have some giant text encoder in there, even though encoders matter, right? And the encoder size matters. So like if you're really trying to push for performance, you really want kind of the biggest image encoder that you can. You want the biggest language encoder, text encoder that you can. But for this type of paper, right, you're not really trying to push the boundaries, state of the art. So the smaller you make your encoders, the faster the inferences. And if you're going to be doing offline RL and online RL, the smaller you can make those encoders, the faster that entire process is going to go, right? Especially online RL, because in online RL, you have to use inference to generate your data that you train on, right? So the speed at which you can generate experience in online reinforcement learning is somewhat gated by the size of your model, right? So if your model is huge and it takes forever to do just one inference step, then the online RL, which is already pretty slow, is going to be even slower, right? Versus if you have a very small model that has very small encoders, then the inference is going to take not a lot of time at all, so you can collect a lot more experience, right? So that makes sense. I appreciate Ed for looking that up for us. All right. So we're in this offline policy training step where we're effectively sampling from our replay buffer of experience, our data set of demo trajectories collected by one human, so our very small data set, using it to create these tuples, and then using those tuples to kind of do very standard offline reinforcement learning, right? So offline reinforcement learning trains a policy, a neural net pi parameterized by theta that produces actions A of t given O of t and z. So basically, you're kind of doing supervised learning, right? You're sampling this from your replay buffer, and you see that this has everything you need to do supervised learning. It has the inputs, O of t and O of t plus 1. It has z, and then it also has A of t, which is what you're going to want to predict, and it has the reward. Right, so literally everything you need to basically push a gradient into this policy is inside this tuple. And that's what offline reinforcement learning is. You're basically sampling, like I think of it as basically supervised learning, right? Because it's like you have this like kind of like static frozen thing and you're just kind of like sampling from it. You know what the input is, you know what the output's supposed to be, and then you just kind of run that. They do add a success bonus to the final reward to encourage reaching the goal. So you can see that the actual reward that is being used to push the gradient is a combination of the learned reward function and then also this kind of like weird additional success, final success. I don't know if I like that. You know, it would have been so much cleaner if they just had it like this, right? That would be the cleaner solution, is like, hey, we just train offline RL using only the learned reward function. Every time you start adding all these like special, like imagine you have this R success and you also have this additional regularization term here and then this other regularization. It's like, once you start adding more and more complexity, I'm generally not a fan of that, but hey, sometimes you got to do it. So how would you train a neural network to perform the best data augmentation? That's an interesting idea, right? Could you train some neural net to choose the type of augmentation such that it's more optimal? Maybe, but yeah, I would say it's kind of a difficult objective because it's like how the baseline is already pretty good, right? Just randomly picking from a set of possible augmentations, right? And possibly combining multiple augmentations, that works fine, right? So if you were to train a neural net to pick that neural net would have to be trained to optimize, like to the loss function for that neural net is like how good is the final thing based on this data augmentation. So it's like the outer loop for that would be like very, very slow. And then every single time you augment, right, one of your samples, you would have to run this neural net that determines what augmentations to use. So yeah, I would say that's the problem with training a neural net to pick the type of data augmentation, is that you're adding in another inference step, right? So yeah, I don't know if it's worth the extra inference step to do that, but I don't know. I haven't done the experiment, so I'm just kind of tacking. Okay. So that's the offline RL, where we're training on our using our learned reward function. And that's the second part of this process. So now let's go to the last part of this process, which is online RL. In online RL, your policy, you can see here that the learned reward function is only trained in this first part. As soon as you have this learned reward function, you basically now freeze it. So for the offline RL and for the online RL, it's frozen in both of these. In online RL, you are no longer kind of sampling from this kind of like cold storage data, right? In online RL, you are interacting with the environment to create the data that you train on, right? So this is kind of why online RL is kind of like the holy grail because it's kind of like the infinite source of data. And usually like there's not as much of a distinction. Usually there's a little bit more of a kind of a continuum where it's like as you collect experience with your policy, you can put that into a replay buffer, and then you can kind of like mix it together with some of your more older data. And then whenever you pull data from that replay buffer, you're kind of, there's a mix in there of like some slightly older data, some slightly newer data. So it's usually a little bit more of a continuum, but here it's explicitly done as two separate phases, your offline RL and then your online RL. And in your online RL, this reward function is now capable of giving you kind of immediate reward per frame, which is kind of unique, right? This is actually unique because a lot of times the reward in a reinforcement learning environment is only possible at the end. You know what I'm saying? So if you're doing a math question, right, all of the intermediate steps, you're not really getting any reward signal. You have to wait until the very end when you're like, and my answer is B. And then you say, okay, was that answer correct? Okay, you're going to get a reward of 1 for that final answer being correct. And then we're going to use some kind of gamma to back propagate that reward through all the intermediate steps. But you have to wait effectively till the end until you can verify that the answer was correct. But here, because we have this learned reward function that gives us this dense 0 to 1 normalized reward, and it's doing it at every single step, right? So it can give you a reward halfway through. So this is a very good fit for online RL, right? So that's kind of the magic, right? Is that you can get a dense reward signal at any point in the trajectory. So it's the combination of these 3 things in sequence, right? So this is the online RL. The online RL also has kind of this weird R success, and they talk about here, success bonuses can come from a human supervisor, a learned function, or an LLM. So they're kind of leaving room here for future work in where you can have more terms in this reward function beyond just this learned reward, right? So maybe you have a human that can observe the robot performing online RL and occasionally can like hit a button and that button gives it reward. The problem with that is that now you have to tune the magnitude of that reward, right? So like let's say that the reward that you can give the robot by pushing the button is extremely high compared to the reward it gets from the learned reward. If you do that, the policy is going to kind of become obsessed with all the actions and observations that were around whenever you click that button, right? Which you might not want, right? So you're going to have to kind of tune the magnitude of these like success bonuses depending on the reward environment or this learned reward that is coming into the robot frame by frame. So that's why I feel like these extra terms are a little bit more fragile, but I think it's a way to add more richness to this reward function, especially if you're going to have a human watching the robot. Okay. Open Room XYZ. Dude, you got so many ideas. You should have like a Substack or something, Open Room. Like a Substack or something. Maybe you should have a YouTube channel where you just kind of like talk about stuff because I feel you got so many ideas here. We should just go wild with data augmentation, basically turn data into noise almost and force this way the neural net to get the best from the data. Yeah, so you're kind of riffing on some of the previous ideas that we've explored where diffusion has this kind of baked in data augmentation because you're kind of adding noise, removing noise. And that's very similar to kind of this where it's like kind of like a dense type of data augmentation where there's like a lot, right? You could have just rewinded here. So just one frame over, now you have a slightly different trajectory with a slightly different reward, right? So that's kind of what I mean by dense data augmentation. And I would classify the implicit data augmentation in diffusion models as a similar kind of a dense data augmentation strategy. Okay. So that's pretty much most of this paper. There's some more interesting kind of results here. So that's the main method section. Then we go into the actual experiment sections where they compare this to other similar papers and they kind of show how it performs well and so on. But I did want to show this because this is this this is more convincing to me than this, right? So here they say, okay, we improve baselines by 2x in simulation. Like, I'm not reading too much into that, right? Like, those are generally kind of pseudo bullshit a little bit. But this one here is interesting. So what they do here is these are different video language kind of like models. I don't know how to call them, but what you're seeing here is these squares. And in this square, on the X and Y axis are basically the different class labels and then the different videos. So whenever you see this diagonal pattern here, what's happening is that the model is capable of saying this video corresponds to this label, right? And this video here is not this label, and this video here is not this label, right? So you can see that all this white space means that the model is capable of saying, okay, well, this is not the right correspondence here. Versus you can see these other ones here are much more confused, right? So rewards for all combinations of demonstration videos and language descriptions. Rewind, which is this paper, produces the most diagonal heavy confusion matrix, indicating a strong alignment between unseen demos and instructions, right? So unseen videos, so it's not like they're literally just using their existing data set that they trained on, right? That would be very bad practice if you're literally evaluating on your training data. So this is an unseen videos, and you can see that the rewind is much better than these other ones and not confusing. So it really has a good understanding of like, this is the task, this is the video, are you completing this task in this video? Right? So it is the most diagonal heavy confusion matrix. I think this result is kind of pretty cool. Granted, I don't know like how strong these other baselines are, but there's very clearly something there. Okay. Let's also talk about this. All baselines are image conditioned. This is the actual arm that they use, a bimanual Koch V1.1 robot arm setup. Kind of interesting, you know. That's probably why it's a May paper. I feel like if this paper would have been released later, it's probably going to be the SO100 robot or SO101 robot. I kind of like that the robot hardware is being standardized around that, right? The little Hugging Face robot, like Hugging Face robot. Like, people don't realize how much of a good idea these little SO100 arms were because they've kind of become a standard. So if every single robotics paper is publishing results on these, it makes it much easier for everybody else to kind of duplicate those results, right? And ultimately, like, peer review is the cornerstone of science, right? You can't have science if other people can't take your results and replicate your results. And that's been a huge issue in robotics because every single robotics paper was usually done on someone's custom robot that is only available in their specific lab, right? So it was almost impossible to replicate other people's works because everyone was using slightly different robots. But because Hugging Face created this very low-cost robot that anybody can make, anybody can purchase, we're now seeing this kind of like change in robotics where everyone can now replicate everyone else's work, right? If you have this robot at home, you can run Small VLA and Pi 0 and Pi 0.5 and Groot, and you can literally compare them, right? Versus even just a couple years ago, it would have been much more difficult to do that because you would have had to adapt every single one of those techniques or every single one of those models to your specific embodiment, and then there might have been all kinds of weird reasons why one doesn't work and this other one does work. So, I don't know, maybe just a little side tangent to talk about how I really like the kind of like low-cost democratization strategy that Hugging Face is doing for robotics. Chinese is coming a long way in standardizing robotics too. Yeah, that's very true as well, right? Like, for example, the Unitree humanoid, a lot of people using the Unitree humanoid. So, similar kind of effect. All right. I think there's a couple more things I had highlighted here. Here's an ablation study. This one was the results here were a little bit weird and confusing, but basically in an ablation study, right, you you kind of slowly remove each of the different components of your system, right? So most machine learning papers, there's going to be kind of like this systems element to it where it's really the combination of like maybe 5 or 6 different techniques, and you're kind of bundling them all together to get some final result. And whenever you do that in any kind of scientific process, it becomes very difficult to attribute the final result to which particular part of that. So the whole point of an ablation study is to try to figure out which parts of this full system are leading to the most success, right? So here they have, for example, the rewind, but without the specific environment data. So their little demonstration data. Rewind without the OpenX data, right? Which is this kind of like more generic, kind of like pre-training data set with much larger variance, much larger size. They have the same thing minus the instruction generation. So minus this kind of text augmentation, right? So you can literally see the effect of the text augmentation, right? So for example, here, instruction generation, you remove that text augmentation, and then you can literally see that 0.79 drops down to 0.66. But here, 1-to-1, right? So within the training demos, so within the distribution of your training data, if you evaluate in that training distribution, then whether or not you augmented the task description actually doesn't matter, right? It gets 100% success because it's literally trained on that, right? But for unseen demos, right, now you're going to be giving your policy a task description, which is some string that it has never seen before, right? So whenever you're giving it a text that it has never seen before, now all of a sudden it becomes quite important that you augmented the text, right? Which is why you see such a huge pop here, right? Similar kind of thing here, right? So look at this. What is the other lowest score here in unseen demo? It's OpenX subset, right? So as soon as you try to take your robot policy and you try to evaluate it in a unseen task, basically some new part of the task space that isn't part of the training, the two most important things are, did you use a large varied data set to train this reward function, and did you augment the text task descriptions? So those two check out. That makes a ton of intuitive sense, right? The part that makes slightly less sense is when you start going over here with policy rollout ranking and input robustness, you start to get these like weird patterns here where minus target env data drastically lower, like, and some of these are even higher. Like, look at this. Input robustness, you get a higher score than the original. I'm like, what? I don't know. These made sense to me. Some of these make sense to me. Some of these are kind of a little bit weird, but either way, I'm glad that we get to see this little ablation experiment. Here's some comments from the team. Using only the small data set, or using only the large kind of varied OpenX dataset without the demo dataset leads to poor alignment with training demonstrations and fails to distinguish between failed, near successful, and successful policy rollouts. Meanwhile, removing the OpenX subset, the kind of large dataset, harms unseen task reward alignment and input robustness, highlighting the importance of the large general pre-training data for generalizing across varied language instructions. And this is effectively the group data pyramid all over again, right? So we saw this in the original group paper where they basically created this concept of a data pyramid where anytime you're training a robotics model, right, you want to have this kind of pyramid of like very wide, varied, high variance kind of pre-training type data, and then slowly constrain or narrow it into the task that you want, right? So this idea of generic to narrow, right? Broad to narrow. And that's exactly what's happening here with these as well, right? You're seeing basically broad and narrow, right? And then in this ablation study, you can literally see the difference between, okay, you can remove the narrow, what happens? Remove the broad, what happens, right? So I think that's just another good data point to validate our intuitions of the importance of having a wide variety of data and organizing it in this kind of curriculum type method where you're kind of starting from the most broad and then ending in the most narrow. Okay. Google account. That's a great YouTube name. Can't wait for the off-the-shelf robotic servos like Steppers. are available. Talking about stepper motors. I don't think stepper motors are super popular in robotics, but I don't know. I'm not super plugged into the whole like motor supply chain and like where that's all going, to be honest. Using pre-trained vision and language embeddings, we do not fine-tune these embeddings, and we found that fine-tuning sometimes hurt generalization performance. So this kind of makes sense, right? So basically they're saying that these pre-trained backbones that are frozen, the Dino V2 and then the other one here, All Mini LM L12 V2, when they freeze them, that basically means that when they're training this reward function, or this reward function, the gradients are getting pushed into this MLP is getting the gradients, this cross-modal sequence aggregator is getting the gradients, but the gradients are not going into the backbones. You could unfreeze them and then let the gradients go all the way through the backbones, and that would kind of overfit the backbones and move them towards your specific task at the cost of losing some of the generalization of those backbones. So sometimes that's worth it. Sometimes it's not worth it. And in this case, it's not worth it. I think it's also because they're very small, right? So like if you start pushing gradients into a very tiny model like that, you're very quickly going to just like scramble the brain. Here's resets are obviously a huge issue. Okay. Here's a little more detail on the actual architecture. So you can see this is basically just a transformer. It's 4 blocks of 8 multi-head attentions and then feed forwards. Pretty standard linear projection as well here to take what's coming out of these encoders and turn it into these tokens that you can feed in here. And then you have your final, kind of almost like a classic model head, if you want to call it that, where you regress to a single final output. Max Malley, this shit sounds expensive to research. What are some of the costs related to training on video? You are 100% correct that training on video is significantly more cost expensive and takes significantly more compute than not training on video. And I remember when I was doing robotics research, I remember my advisor being like, I wanted to obviously use image input, right? And I was like, okay, well, definitely we're going to have some image input. And he's like, if you use image input, it's going to take 10 times longer to train, and your results are going to be worse because it's just not going to work as well, right? So there is truth in that. And that's why a lot of classic robotics stuff was usually done with states, right? So like proprioceptive states, and then maybe you explicitly track the position of the robot with some kind of like multi-view camera type setup. And then that's what you're actually feeding into the neural net. It's not like images or observation sequences, but you're literally just feeding it like states. And whenever you do that, right, the lower dimensionality of states means that you can do inference faster, you can push gradients faster, the model is smaller, you can do it more in parallel, so you can train faster. Versus as soon as you go into the image or observation space, that image needs to go through a ConvNet or a vision transformer, and it's going to take slower, right? So your inference is now slower, your model's now bigger, every gradient push takes longer. So yeah, the difference between using images and not using images is definitely huge, but in real world robotics, like you kind of have to use images, right? You can't depend on like some mocap system to give you the state of the robot. I prefer the artificial muscle road, but we are not there yet. Yeah, so have you guys ever seen this one? These guys are known for their entirely different strategies. So they have this robot, right? Which is like these kind of like artificial muscles. I'm not exactly sure. I don't know if it's like some combination of like tendons and like hydraulic. So it's like water pressure and tendons or something like that. But here's the reality, guys, is that I don't think these guys survive there's a bubble pop coming, right? So we're in an AI bubble, and it's going to pop kind of like the 2001 internet bubble, right? So I don't know exactly when that's going to happen, but if I had to guess, within the next year to 5 years, there's going to be a bubble pop moment, and a lot of these startups are going to disappear, right? So whenever I look at this clone robotics startup, I've never seen a demo from this that is anything beyond just like this type of stuff, right? Like every single demo I've seen from this company is like this like weird thing that like kind of like twitches and is like, this thing doesn't even walk yet. This thing is not folding napkins. This thing isn't doing anything. And if you go to their website, these are all just renders. You know, like that's not the actual robot. This is like a 3D render. They paid some artist to create this 3D render because their robot doesn't actually work. So even though it's a very cool idea, and I'm glad that there's humans that are exploring the space of actuators to find interesting ideas, I don't have a lot of trust in this type of company surviving, right? Because the reality is that ultimately startups and companies, they need to make money. It's already very difficult to make money as a robotics company. If you're doing like this type of super researchy stuff and you literally have zero income because everything you're doing is effectively like deep tech research, it's going to be very, very difficult to survive the bubble pop. Anastasia in Tech has a video on them. Yeah, I saw it. And like I said, I think these people are really cool. Like I applaud what they're doing. I just, I have the honesty to tell them that like, hey, once the investors stop investing, it's going to be very difficult for you to turn a profit. You're probably going to end up firing half your team, which is going to get pretty dark pretty quick. Okay. Let's go back here. Dino V3, again, I mentioned because they're using Dino V2, you could just plug in Dino V3 and get better results. And another thing they could do is have more video augmentation strategies, right? So in this one, they really only use this rewind, but we looked at these other papers that come from video action recognition, and they have a much broader set of video augmentation. So I think you could literally take this paper, plug in Dino V3, increase the different types of video augmentations, and you could get an even cooler result. I'm waiting for all the secondhand humanoid robots to make their way to eBay garage sales for parts. Yeah, sometimes that happens, Like after the 2001 bubble pop, there was a lot of cheap servers that you could buy. Okay. Oh yeah, okay, let me go back to this. So this is a very interesting paper, and I was in Google Brain when this paper was, and look at some of the people on here. This is the 1X guy, and this guy is the figure guy. And then you got Sergey in here. You got some like heavy hitters here. So, but this paper is super interesting because it's kind of similar to this, where you're using kind of the symmetries of time, right? So time has interesting symmetries to it, right? And in this paper, they're largely using the fact that you can reverse time to basically create an augmentation for videos that allows you to get unsuccessful trajectories. In this one, they're doing something a little bit more crazy, but it's a really, really cool idea. It's using contrastive losses in time from multiple viewpoints. Okay, so it gets a little complicated, but let's dive into this. Time contrastive networks is a self-supervised approach for learning representations and robotic behaviors entirely from unlabeled videos recorded from multiple viewpoints. So multiple simultaneous viewpoints of the same observation are attracted in the embedding space while being repelled from temporal neighbors, which are often visually similar but functionally different. Okay. So what is happening here is that you have a video of someone pouring in this case, a coffee into a cup, right? And you have that same person pouring coffee into a cup, but from two different views, right? So you have like this video view and this video view. So it's like the same video, but two different views. So what time contrastive networks do is they're basically using a contrastive loss, right? Which is similar to the clip, right? If you've ever seen clip, right? You've definitely heard of clip. That's the same kind of contrastive loss. And in a contrastive loss, right, you're bringing things together and then you're repulsing things. So you're basically saying, okay, in these two videos, even though these two images are from different views, they are representing the same thing, right? The same point in the same trajectory where the cup was the same amount full with the same liquid and everything. So really, when you embed this image and turn it into this embedding, that embedding should be the same for both of these images. Okay. But the embedding should be different from the embedding of this frame, even though it's from the same viewpoint, because it's further on along the trajectory, right? So you're basically pulling together the embeddings for things at the same point in time, and then pushing apart the embeddings for the things that are further in time, right? So you're using this contrastive loss to kind of pull things together in the temporal dimension and push things away as they are further apart in time. And what that does is it creates this model, which or this embedding, which allows you to then do this type of self-supervised imitation learning, right? So it's actually very similar to this idea, right? Where you can get kind of like a denseness because time has these kind of symmetries, right? This is a little bit older. In this case, they're not actually training a policy, right? What they're training is this TCN embedding, and then they use that TCN embedding in some kind of, I don't even know exactly what. I think it's just like straight. Might not even be RL. That's what I'm saying. It might not even be RL. This kind of looks like RL. Let me see. PILQR. What is PILQR? Okay, I'm not entirely sure what the learning method for actually using that on the robot for this is. I don't remember, but the important idea here is this thing here, is this kind of idea of things in time that are close together are similar, and things in time that are further apart are dissimilar, and that property exists regardless of multiple viewpoints, right? So you could do something very, very similar with this, right? In this case, there's just one viewpoint, but you can imagine adding more viewpoints and then having some kind of augmentation or some kind of additional signal here where the reward should be the same from this viewpoint than from this viewpoint at this time step, right? The reward at this time step, if those two time steps are the same, should be the same versus this time step and this time step from different viewpoints. So it's kind of like, it's almost going to the idea that you had OpenRoom XYZ of like having 100 cameras all recording the same robot doing the same thing in order to kind of use that multi-view kind of augmentation to ultimately then train a learned reward function, which you can then use in a offline RL or online RL setting. Coming from Poland, creepy stuff. You're talking about the weird clone robot. I'm waiting for all the secondhand humanoid. Okay, I think we already answered that. Let me see if there's anything else that I highlighted here. TCN embeddings provide a way to extract image features that are invariant to the camera angle and the manipulated objects and can explain physical interactions in the world. We use this insight to construct a reward function that is based on the distance between the TCN embeddings of the human video demonstration and camera images recorded with a robot camera. So again, literally, actually this exact same idea, right? This reward function. You learn this reward function by using this kind of augmentation, kind of like bias, inductive bias that is based around time. You know, what's old is new again, and this 2018 paper is now kind of being repackaged in 2025. What about here? Is there anything else I wanted to show here? I think we already saw that. Oh, something interesting that I thought about here. So invariance to temporal reverse order. So for example, in this one here, right? I think this one, for example, when you reverse the order of time, you are now reversing the label, right? So opening becomes closing, right? And in this case, it's a little bit, it might be difficult to kind of know. So like, what is the opposite of opening, right? You don't necessarily know that. So like, even though you're getting a new data point here, you have to effectively label that data point yourself. But I wonder if you could do this in a more automated way, right? I wonder if you can use a vision language model that and basically say, okay, if I take this video and I reverse it and the label of this video is opening a box, what is the label of the video when I reverse it? I'm pretty sure most VLMs will correctly guess, oh, this is closing the box now, right? So you could use this type of reversal and then use it to change the text description, right? So they're not doing this at all in this paper, right? In this paper, they're just using the video reversal to have a different reward for different parts of the trajectory. But ultimately, the task is still the same, right? Whether you reverse the last 20% or you don't reverse it or you reverse it from starting here, like the text description is the same. But you could imagine something a little bit more intelligent where if you reverse the entire video, you change the text description, right? So I think there's another kind of clever potential augmentation you could do here using VLMs that have this very good world understanding to automatically change the label depending on the type of reversal that you do in the video frame space. I don't know if that makes sense or not. Maybe. All right. This paper was actually crap. I thought this paper would be related, but it's not related at all. Okay. I feel like I just blasted through everything. It's only 10:50, so we haven't even gone for that long, but I don't know what else to talk about, so let me scroll up on these chats, see if anybody wants to say anything else. Reversing time entropy becomes neg entropy, so our physics, not our physics anymore. Yeah, I mean, time is weird, right? Let's see. Open room, XYZ, Ed. Okay, I don't think anybody answered or asked any other stuff, so I'm just going to kind of do a quick summary here, and then we'll just end it there. I got a bunch of stuff to do today, guys, so keeping this one short. Max Malley, just throw every in the training data, multi-viewpoints, reverse videos. Yeah, I'm all in on data augmentation. I'm like a data augmentation hype train. All right, so today's stream was called Language Guided Rewards. This is a paper recommendation from this underrated RoboPapers podcast, which is referencing this paper here called Rewind Language Guided Rewards, which is a clever little paper that basically has one important idea in it. And the important idea is using learning a reward function that gives you a dense signal, right? So a dense 0 to 1 normalized reward for policy training, and then learning that reward function from a very small data set, D demos, 15 to 20 tasks with 5 demonstrations each, and then using a clever type of data augmentation in the space of frames by using video rewinding, which allows you to create somewhat infinite trajectories from your initial small data set of trajectories that have a much more nuanced reward over time, right? So like if you were to just have your trajectories that you collected, they would all just basically start at 0 and then go up to 1, right? And you would always have this like same monotonically increasing thing. And what would probably happen is that your learned reward function would basically just overfit to the position embeddings and then basically see like, okay, if you're at the beginning of the video, then it's going to be 0. And if you're at the end of the video, it's going to be 1, right? But by having this data augmentation where they like randomly reverse halfway through the video, you now start to have a lot of examples in your training data for your reward function where the reward goes up and then suddenly the reward goes down. And that means that now this reward function, it has to actually learn, like, it has to actually learn to understand what is actually happening in the video and like, is this actually getting me closer to my goal or not getting me closer to my goal, right? And because this is a very general reward function, right, all it's taking is just a sequence of observation images and then a text description, this reward function can now be used to provide a dense reward signal for offline RL and online RL on new, unseen, potentially slightly different tasks from your original training distribution, right? And it's a powerful idea. It seems to work pretty well. And yeah, maybe it's not necessarily a super new idea because we found some other papers here that have very similar kind of concepts, such as time contrastive networks, which is a banger of a paper that came out a while ago now, but similar idea, training a reward function, in this case using a contrastive loss in multi-view images of the same sequence. We also looked at a couple different video action recognition papers, so completely different world from robotics, but these people have also explored the space of video augmentations much more thoroughly than robotics people, right? So these guys, they live in the video world, so like everything they do is video, so they figured out pretty much every single type of video augmentation that doesn't change the class label, or in the robotics world, a video augmentation that doesn't change the task description. And yeah, I don't know, I just thought that was a kind of a cool idea. You know, I love thinking about time. I think time is kind of a very interesting concept. I think it has like all kinds of interesting mental threads that you can go down when you think about time. And I don't know, I just thought this was a cool little read. Hope you guys enjoyed it as well. Thank you, Google account, Max Mali, Saskia Sound, or Saskia Ludden. Who else? Open Room XYZ, Ed, Count Duz, Mark B, and James McLean. Thanks everybody for hanging out. Hope you guys had a good time, and hope you guys have a good weekend. See y'all later, guys.